Hi, I'm Becky Alexander, an atmospheric scientist working at the University of Washington. I study the way our atmosphere is impacted by the energy sources we use to power our society. When I'm not studying the atmosphere, I enjoy skiing in the winter and hiking in the summer. I also love spending time with my 2 kids, my husband, my mother, and my 2 cats. As an atmospheric scientist, I spend my career looking at how the thin envelope around the Earth is changing. The news is constantly filled with really depressing projections about the way humans are changing the atmosphere and climate. We hope that this video series is different. We actually made this video series specifically to share some of the data that we have discovered that provides hope for the future. The data we'll analyze in this series come from ice cores, from satellite measurements, from airplanes, and from land-based measurements. In each episode, we'll narrow in on data from the last century and what it can teach us as we look for a hopeful path into the future. In the first episode, we'll analyze the impact of how we have chosen to make electricity. In the second episode, we'll look at the impact of our transportation choices. Most exciting will be the third episode, where we'll look at data from the ice cores I just drilled in Greenland. These new ice cores contain data that might provide some hopeful signs for the entire aquatic ecosystem of the North Atlantic. So let's get started with the first episode, where we'll look for hope in how we generate electricity. Specifically, we'll analyze the impact that environmental laws that were passed in the last century had on the composition of the entire atmosphere. Let's write this investigation question down in your notebooks. How much impact can electrical generation-focused environmental laws have on the atmosphere? So I'm going to turn this over to Drew and Zaina, 2 of my students here at the University of Washington. Drew and Zaina are responsible for running our lab and generating the data that you'll be analyzing today.
Thanks, Becky. I'm Drew.
And I'm Zaina. We're both students studying atmospheric chemistry here at the University of Washington. A lot of the data that we'll analyze with you in this series is generated in this lab, as well as labs like ours at colleges and universities around the world.
When we need data from the past, we turn to the ice in the glaciers of Greenland and Antarctica. We can pull a ton of great historical data from the tiny gas bubbles that form when small samples of the atmosphere get trapped as the snow transitions to ice.
The question Becky asked us to analyze was if passing environmental laws related to how we generate electricity can actually positively impact our atmosphere. To answer that question, we're going to have to pull together a lot of data.
Let's make a data table in your notebooks to record the data we'll analyze in this episode. We'll be looking at data for each decade, beginning in 1900 and ending in 2020. To start, we should probably look at how much electricity the United States made in the past by burning coal.
In the late 1800s, when the United States first began to produce and distribute electricity, most of that electricity came from small-scale hydroelectric generators. That changed quickly around the turn of the century. As more electricity was needed, the United States turned to burning coal for most of its electrical power. Coal at that time was cheap and abundant, and very few people thought much about the long-term environmental impacts of all that pollution.
Here are good estimates of the terawatt hours of electricity produced each year by burning coal in the year starting each decade. Pause the video while you transfer these data to your graph. Make sure to include a best fit trend line or a curve that you think tells the story of the data. When you're finished, hit play again, and we'll start to look at the impacts that burning all of that coal had on our atmosphere. Welcome back. That data is really interesting on a lot of levels. You might be wondering why the amount of coal being burned to make electricity began to drop so much after the year 2000. What you're seeing is the world beginning to transition away from coal to cheaper, less harmful energy and clean energy alternatives like wind and solar, as well as the somewhat less harmful natural gas.
It takes about 6,000 train cars of coal to produce just 1 terawatt hour of electricity. That means since 1900, we have literally burned millions of train cars full of coal and released those emissions into the atmosphere. When coal is burned to make electricity, the products include mostly carbon dioxide and water vapor. There's also smaller amounts of chemicals released from the impurities that you find in coal. One of these impurities, sulfur, reacts with oxygen and water vapor in the atmosphere to produce sulfate ions, a major component of acid rain.
Ice cores retrieved from the Greenland ice sheet contain samples of the atmosphere in tiny bubbles trapped in the ice. These samples of atmosphere go back hundreds of thousands, even millions of years. By analyzing the chemical composition of the ice cores, we can directly measure how humans have impacted the composition of the atmosphere. When we analyze the atmospheric samples in the ice, we start by figuring out how old the ice is, which we do by counting the visible annual layers of ice. We can then take ice from different years in the past, melt that ice, and measure the amount of pollutants, like sulfate, that were in the atmosphere when the ice formed.
The technique we use in our lab involves melting the ice and pulling the melted liquid into our ion chromatograph. The ion chromatograph produces a large bump in signal when sulfate ions are detected. The area under this large bump can be used to estimate the amount of sulfate that was in the atmosphere.
Here are the data we pulled from ice samples beginning in 1900 all the way to the present. Sulfate levels can be affected by humans, as well as naturally occurring events, like volcanic eruptions. For this reason, the amount of sulfates that we measure each year in the ice can vary quite a bit. To make it easier to see the overall trends, we can do some statistical smoothing.
Let's smooth the data by finding the median sulfate value using the 3 years around the start of each decade. For example, in the 3 years around 1900, 1901 is the highest value at 41 parts per billion. 1900 has the lowest value at 24 parts per billion, and 1899 represents the middle, or median, value at 38 ppb. Let's record the median of 38 ppb for the approximate value of sulfate around the year 1900. Let's calculate one more together. Let's analyze the 3 years around the year 1910. The highest sulfate value here is 48 ppb in 1911. The lowest sulfate value here occurred in 1909 at 42 ppb. For these 3 years, 1910 has the middle, or median, sulfate value of 45 ppb. Let's add 45 ppb in 1910 to our data table.
Next, I'll scroll through the 100 years of sulfate data from 1920 to 2020. I'll pause for 5 to 10 seconds so you can calculate the median value based on the 3 years around the start of each decade. If you need more time, just pause the video. Welcome back. Here are the median values that I calculated for each decade. You can check to make sure that we both calculated correctly. Next, let's move our data to our coal graph to see if there's a relationship between how much coal we were burning and how many sulfate ions were in the atmosphere and trapped in the ice. We can put the sulfate concentrations on the other y-axis using a different color and a different scale. Pause the video while you plot your sulfate data on the same graph that we used for the coal. We can use the other y-axis for sulfate levels in the atmosphere. When you're done graphing, make sure to include a trend line that you think shows the story of the data. When you're done with all that, hit play again, and Becky will join us again to see what story she sees in the data.
Welcome back. As an atmospheric scientist, these data look super interesting to me. Here's what my data looked like when I plotted them on a graph with the coal electricity generation data on it. In the beginning, the data all seemed to make logical sense. As we burn more coal, there was more sulfate trapped in the ice, which means there was more sulfate present in the atmosphere. This relationship was very consistent until about 1980. Then the data go in different directions. We call this decoupling. When we see the data decouple, the question then is, what caused the coal and sulfate data to decouple after tracking so nicely for over 50 years? The answer, I think, can be found in the halls of Congress and the Nixon White House. In 1970, the Bipartisan Clean Air Act was passed by Congress. This huge piece of legislation was designed to reduce pollution and improve our nation's air quality. Laws to reduce sulfate and the acid rain it produces were included in that legislation. Let's add a line on our graph to show when the Clean Air Act was passed. Over the next decade, the electricity industry began to change to comply with the new requirements of the law. Engineers designed systems called scrubbers that were fitted onto coal-fired power plants to trap the sulfate before it could get into the atmosphere. Over the next 30 to 40 years, the amount of sulfate in the atmosphere began to drop, and drop fast, even though we were burning even more and more coal to make electricity. Even before we started to move to other energy sources to make electricity around the turn of the century, the amount of sulfates and acid rain in the atmosphere were back to around the levels that existed in 1900. This was a major legislative success. Forests that were dying from acid rain pollution rebounded, and problems caused by acid rain decreased. This reduction in sulfate also had other benefits to human health, since sulfate is a major contributor to particulate matter. The reduction in sulfates in the atmosphere moved the needle in a positive direction on respiratory, cardiovascular, and neurological health. This evidence we've collected here suggests that when we act together to pass major environmental legislation, we can make a measurable positive impact on the atmosphere. These positive impacts can be measured even in places like Greenland that are really far away from the United States. These are the kind of data that really give me hope for the future. Before we wrap up this episode, let's add one more set of data to our graph. Let's add a pollutant to our graph that was not included in the Clean Air Act of 1970, carbon dioxide. I'll pass this back to Drew and Zaina, and they can help you add carbon dioxide, a pollutant not controlled by the Clean Air Act of 1970, to the graph.
When all fossil fuels burn, they release carbon dioxide and water vapor as the two major products of the combustion reaction. The water vapor is rapidly removed from the atmosphere as precipitation. However, the carbon dioxide stays in the atmosphere for thousands of years.
Since around 1960, scientists have been directly measuring the amount of carbon dioxide at a weather station on the top of Mauna Loa in Hawaii. We can use their direct measurements from the atmosphere to fill in our data table with carbon dioxide levels between 1960 and 2020.
Before 1960, nobody was constantly measuring the amount of carbon dioxide in the atmosphere. Lucky for us, we have glacial ice that has been trapping samples of the atmosphere for us for over 1 million years. When snow falls in places like Greenland or Antarctica, it traps small bits of the atmosphere between the snowflakes. As the years pass, more snow falls, and the pressure compacts the snow and changes it into ice. The atmospheric gases that were in the snow get trapped into small bubbles that are preserved in the ice. If you want to learn more about how some really cool engineers drill and analyze the ice, scan this QR code.
In our lab, we melt the ice cores brought back from Greenland and Antarctica on a continuous melter that allows us to measure many different kinds of chemicals down to the parts per trillion level. Here's a data set of the carbon dioxide levels we measured using samples of gas from bubbles trapped in ice between 1900 and 1960. We can use these data to fill in the missing years on our table.
The carbon dioxide data pulled from the ice cores is shown as the median value of the 3 years around the start of each decade, just like the sulfate data. What's really cool is that there's overlap between the carbon dioxide measured from the ice cores and the direct measurements made in the atmosphere in Hawaii. The measurements from the ice cores are mostly within 1% of the Hawaii measurements. This reproducibility gives us a lot of confidence in the measurements we make of the atmosphere using the gas bubbles trapped in the ice.
Remember, the goal here is to plot a pollutant that was not controlled in the 1970 Clean Air Act. I think if we use a different color, we can add a second y-axis to the right side of the graph. Let's add a scale that will work with our carbon dioxide data and plot the CO2 data in a different color. Pause the video while you plot the carbon dioxide data. Make sure to include a trend line that you think best represents the story of the data. Welcome back. The graph is pretty busy, but I think it tells an interesting story. Let's finish by writing 2 things that you notice about the data and 1 thing that you wonder. Pause the video 1 more time while you write. When you finish, Becky will come back with her final thoughts.
Thanks, Drew. Thanks, Zaina. When I look at this graph, I really see a story of hope. One bipartisan piece of legislation, passed way back in 1970, had a positive, measurable impact on the amount of sulfate pollution in the atmosphere. It only took a few years after passing that legislation for the composition of the atmosphere to begin to change for the better. Unfortunately, carbon dioxide was not included as a pollutant in that 1970 legislation. Instead of reducing the amount of carbon dioxide in the atmosphere, the United States and the rest of the world has actually been accelerating the amount generated. We have started to generate a lot more of our electricity from wind, solar, and other carbon-free sources. But unfortunately, we have also increased the amount of natural gas being burned to make electricity. And we continue to rely primarily on fossil fuels to power our transportation industry. The impact of these decisions is easy to see on this graph. Carbon dioxide levels are now higher than they have been since humans began to roam this earth. The result is that now our planet is heating up quickly and entire climate systems are changing. But this graph still does give me hope. Just like in the 1970s, we can change the future composition of our atmosphere by passing laws that limit carbon dioxide and other greenhouse gases by promoting a rapid transition to a clean energy systems. The data analyzed in this episode really tell the story of our choices. It is now up to my generation, Drew and Zaina's generation, and you to choose a path forward that will reduce carbon dioxide levels in the future, just like we reduced sulfate concentrations in the past. Fortunately for us, we now have the technology to make that choice. We just need to get the bipartisan legislation in place to guide us forward. Thanks for joining us for part 1 of this series, where we were looking for hope on a warming planet. Come back for episode 2, where we'll focus on the impact of our transportation system. See you there.